The finding could shed light on how impacts can reshape the faces of planets and how such collisions can generate new habitats for life, the researchers said. Asteroids and comets occasionally pelt Earth's surface. Still, for the most part, changes to the planet's surface result largely from erosion due to rain and wind, as well as plate tectonics, which generates mountains and ocean trenches, said study co-author Sean Gulick, a marine geophysicist at the University of Texas at Austin. The key driver of surface changes on those planets is constantly getting hit by stuff from space, Gulick told Live Science. The researchers in the new study looked at Earth features to learn more about impact effects found on other solar system objects. Major craters sometimes possess rings of rocky hills in their centers. Most of these peak rings exist on extraterrestrial rocky bodies such as the Moon or Venus, making it difficult to analyze these structures in detail and pin down their origins. So to learn more about peak rings, scientists investigated a gargantuan crater on Earth that measures more than 110 miles (180 kilometers) across, located near the town of Chicxulub, in Mexico's Yucatan Peninsula. The researchers focused on the Chicxulub crater because it has the only intact peak ring on Earth. In contrast, larger craters on Earth, such as Sudbury in Canada or Vredefort in South Africa, have been heavily eroded. Neither one has peak rings anymore, Gulick said. On the other hand, Chicxulub's peak ring is completely preserved. The structures that the researchers wanted to examine were under about 60 feet (18 meters) of water in the Gulf of Mexico. They showed evidence they experienced a high degree of shock from the impact. After the impact, the Earth there would have temporarily behaved like a slow-moving fluid, Gulick said. The stony asteroid would have opened up a hole probably almost the thickness of Earth's crust, almost 30 kilometers 18 miles deep, and on the order of 80 to 100 kilometers 50 to 62 miles wide. At the same time, the center of this hole starts reaching upwards, like when you throw a rock in a pond and you get a water droplets rising in the middle, Gulick said. The study's findings support one of the two main hypotheses that describe peak ring formation, the researchers said. One explanation suggested that peak rings originate closer to the surface as an impact causes a peak to form in the middle of the crater. The uppermost part of this peak melts, causing the material to disperse into a ring of peaks. The other hypothesis suggested that peak rings formed because impacts dug deep into their targets. It turns out the models based on the deeper origin seemed to have gotten it right, Gulick said. The model these findings support is based on what are known as hydrocode models, which are used for simulating nuclear bomb blasts. Those models simulate an asteroid impacting a target at close to about 20 km per second, 44,740 miles per hour, which can get the crust to flow. Unexpectedly, the researchers noted that rocks from peak rings got fundamentally altered by their journey upward during the impact, Gulick said. They end up lower in density by a lot, with their porosity increasing from 1 to 2% to 10%. These changes may have proven critical for the evolution of life on Earth and perhaps on other planets, Gulick said. When you get rocks with 10% more pore space, microbial life living below the surface may find new habitats on the surface, he said. Our next area of research involves looking at whether ecosystems can get started by craters.